Gresham College presents X-ray Astrophysics, the High Energy Cosmos by Professor Carolin Crawford, Gresham Professor of Astronomy.
So today, the talk is about X-ray astrophysics. It's one of the new astronomies. It's kind of really taken off about 50 years ago. In fact, we're celebrating 50 years of X-ray astronomy this year. And what I want to show you is how it gives you literally a very different view of the cosmos and some of the events and some of the regions within it that you can only study through the X-ray mission. So we're all armchair astronomers. We're used to seeing these fabulous pictures, taken with some of the biggest ground-based telescopes and space telescopes like the Hubble. But they still show us something that is quite familiar. It's familiar whether you're looking through a telescope with your unaided eye or you're browsing these images in the coffee table books. And they're familiar because they're showing the same kind of things. They're showing glowing clouds of gas. They're showing maybe planets, stars, and where all of that is congregated together into galaxies. And it's familiar because it's all the same waveband, which is the visible. But the visible only shows you a tiny sliver of all the observational matter that's out there, all the stuff that's giving off light. You're only seeing the tip of the whole iceberg. And indeed, there are other lights out there, and they're sensitive to different events. They're producing completely different processes. If you look in the optical, you look at material, probably at temperatures of thousands of degrees. You don't see the material that's at tens or hundreds of degrees above absolute zero. You don't see the material that's at millions or tens of millions of degrees in temperature. And in particular, you're not seeing light from some of the most explosive, most energetic events in the universe. And for that, we're going to have to move to X-ray astronomy. But let's just be absolutely clear what I mean when I'm talking about observing through the light of X-rays. And for that, we have to have a quick introduction or rebrief about the electromagnetic spectrum. So we're familiar with the idea that if you pass visible light through a prism, it splits it into the rainbow of different colours. So going from blue through to red. And what gives the difference between a blue and a red colour is the wavelength. If you think of light as a wave, the distance between features in that wave structure, say from one peak to another peak, or from one trough to the next trough, that's called a wavelength. And red light has a longer wavelength than blue light. And that's your basic characteristic of what determines a colour. But in fact, there isn't much difference between blue light and red light in the visible. Blue wavelength might be 40 thousandths of a millimetre, red light 60 thousandths of a millimetre. There isn't that much distinguishing them. And there are wavelengths way beyond the visible spectrum. You can have wavelengths that go down to subatomic scales. You can have wavelengths up to thousands of kilometres long. And it's those other wavelengths that give us these invisible lights. So if you're going to longer wavelengths, you're moving beyond the red into the infrared, down to the microwave and to the radio. That's where you get these really long wavelengths. And similarly, beyond the blue, you have the ultraviolet, and then the X-rays and the gamma rays. And today, we're going to be focusing on the very short wavelength light that is X-rays. So you can characterise light in terms of waves. If you want a quantum mechanical interpretation, you can also interpret it as particles called photons. They don't have any mass, they travel at the speed of light. And each of these photons carries a discrete packet of energy. And you can characterise these different colours in terms of wavelength, or you can characterise it in terms of the amount of energy that those photons carry. And the energy of the light is inversely proportional to the wavelength. So what this means is that if you have a long wavelength, it's a low energy photon. If it's short wavelength, it's a high energy photon. And this, for the purposes of today's talk, is going to be the most useful description about different lights. High energy lights come from high energy events. Low energy photons come from low energy events. And so you can begin to see why X-rays are associated, as I say, with some of these violent, very explosive places in the universe. Now, all of these are light. They all travel at the speed of light through a vacuum, And all light is, all of the electromagnetic spectrum, is just a way of carrying energy from one part of the universe to another through the sort of varying electric and magnetic fields. So let's just look at what might give off different lights. And if we go to this idea of energy, that would lead us straightforwardly to temperature. Because temperature is just a measure of how much energy, for example, a cloud of gas atoms might have. The hotter they are, the more those particles are moving around, the more energy they have. And so hotter stuff gives off higher energy light than lower temperature stuff. And so if you imagine something that's glowing in the visible, so it's at thousands of degrees. Imagine you're heating up metal. As you progress from just being red hot and you heat up the metal more, the peak of the radiation is going to move from those red lights up towards more the sort of yellower and the whiter lights. If you think of something as being white hot, you think of it as being hotter than when it's just red hot. And so this is a key thing to remember, that in physics, unlike in your plumbing, red is cold, blue is hot, okay? Different way around. But this extends, obviously, if you're just heating up your bar of metal or whatever from red hot to white hot over quite a narrow temperature range. It also extends to stars. Stars come in all kinds of different colours. You've got very massive blue stars, you've got much smaller red stars, yellow stars like our sun. And the colour of the star tells you immediately where it's outputting most of its radiation, which is connected to its temperature. So, for example, very hot stars, giant stars, which are around this region, they can reach surface temperatures up to 20,000 degrees. Yellower stars like our sun span this region about 5,000, 6,000, 8,000 degrees. And the very coolest stars, where their surfaces are at temperatures like 2,000 to 4,000 degrees, are red in colour. And so immediately, if you see a blue star, you know it's a very luminous star, it's a very hot star. The red stars, the yellow stars are less massive, cooler stars like our sun and other dwarf stars like it. But that's just where the peak of radiation in the visible comes out. You can appreciate that there may be some stars that are so hot that they look blue to us, but maybe their peak of radiation is more in the ultraviolet. They're so hot that most of their energy is coming out in the ultraviolet, and we're just getting the tag end, the blue end of that light. And then there are even other materials which, if they're at temperatures of millions of degrees, they're going to produce most of their radiation in the X-rays. So the rule of thumb, an X-ray photon is about 1,000 times more energy than a visible photon. That means you have to heat something up 1,000 times more. So if a visible photon is sensitive to temperatures of thousands of degrees, an X-ray photon is sensitive to temperatures of millions of degrees. Very different parts of the universe. And so just as a very rough temperature scale, if you're in the infrared, like you all are here in the audience, your temperatures of hundreds of degrees above absolute zero, that's cold. You move into the visible as soon as you're in thousands, then you move into the ultraviolet. And X-rays are sampling about 1 million to 10 million degrees above absolute zero. Very different state of matter from what you see in the visible. So, X-rays have been known about for about 110 years. They were discovered in 1895 by Wilhelm Röntgen, who was working in the University of Würzburg as a professor at the time. And the name X-rays just reflects the idea that it was a temporary name at the time to indicate, we don't know what these are. And they showed very different characteristics from other forms of light, even directly from those first images he took in his laboratory. For example, this photograph of his wife's hand. And this is a film exposure, so like a photograph, where it's white, the X-rays have fallen on the plate and exposed the film. Where it's dark, they've been blocked from falling on the film and they haven't been exposed. And so you can see immediately that the X-rays can travel through the flesh of the hand. More X-rays are stopped by the bones in the hand, and most of the X-rays are stopped by the ring on her finger. And so this immediately shows that X-rays can travel through materials which would block other forms of radiation, things which would not let optical light through. So again, more energy. However, they are stopped within just perhaps a few centimetres worth of air, and of course they're stopped by metals and much more, deeper columns of material. And for this discovery of X-rays, I won the first Nobel Prize for Physics in 1901. So this idea that if you have an X-ray source and you have something that absorbs the X-rays along the path, immediately lends itself to our most everyday experience of X-rays, which is in medical or dental X-rays. In astronomy, it's very different. In medicine, you produce a source of X-rays and you're investigating what lies between you and the detector. In astronomy, well, we're interested in what's causing the source of the X-rays. Sometimes there may be absorbing matter in the middle, but that's of secondary importance to what's generating the X-rays in the first place that we detect with our X-ray telescopes. And you've got the idea already that the simplest form of X-rays that we detect is what's called black body radiation from things that are hot. And surprisingly, given what I've just already told you about the temperature range, the sun is quite a bright emitter of X-rays. And this was the first known astronomical object to emit X-rays. And it seems contrary to begin with, because the surface of the sun, I've told you, is yellow, because the peak of its radiation, its temperature is around 5,000, 6,000 degrees. That's why, when you look at this X-ray image of the sun, the disk of the sun is black. It's too cold to give off X-ray emission. Where most of the X-ray emission happens is not at the surface of the sun, but about 1 million kilometres above the sun. There's something called the corona. It's an extended outer halo of the sun, and it's at temperatures of 1 to 2 millions of degrees, and that emits very strongly in the X-ray waveband. And this in itself is a strange observation, because if you think the nuclear fusion that's powering all of the sun goes on right at the core, and then as you get further away from that, you'd expect things to cool down. The fact that it cools down to 5,000, 6,000 degrees at the surface and then heats up again with this outer corona means you need an input of heat, input of energy to heat up this outer halo. And it's thought to be connected, as you can see quite clearly from this image, with regions of intense magnetic activity on the sun. And these are traced by sunspots on the sun's surface. So this little movie pans from a visible image fading right through to an X-ray image of the sun. And you can see the connection between those regions of high magnetic activity, and they're bright in X-rays, and they're feeding through to this outer corona. And it's thought that this magnetic activity in the surface of the sun, the way that magnetic field lines can't cross and they reconnect and they give off energy in this process, that is all responsible for heating this outer corona. But I will say this has been only a relatively recently understood phenomenon. Even though this was the first X-ray source, it's taken us a while to understand why the sun is a strong X-ray source. So that's fine if you've got something that's hot, but imagine you've got a very diffuse cloud of gas that's at temperatures of millions of degrees. It's all the atoms have been broken apart into electrons and ions, so those are charged atoms. So you've just got this big soup of charged particles. If it's hot, they're moving very fast, and they'll have interactions between the two, and these can be a very strong source of X-rays. And there's a process called Bremsstrahlung, which also stands for breaking radiation. So you have this cloud of high-energy particles, and you imagine you have an electron minding its own business, whizzing around. If it comes to within the electric field of a proton, imagine it comes near enough to just deflect its path and curve round. You're accelerating the electron, you're giving it energy, and it releases this energy in the form of a photon. Now, the amount of energy it gives off depends on how fast the electron's moving, the strength of the field it's moving through. And X-rays are going to be very, very strong in very hot plasmas where particles are moving around a lot more. And it's electrons that are key here. I mean, obviously, this will happen for all kinds of particles moving under the electric field of other kinds of particles. I'll just remind you of some O-level physics. Force equals mass times acceleration. If you have a given electric field from a particle, the smaller the particle that's being accelerated, the larger energy that's being given off, the higher energy the photon that's being given off as that excess energy is released. So therefore, X-rays primarily emitted by electrons being whizzed around by the charge fields of atoms. And this becomes very important when you have large clouds of gas. So some of you may have been to my talk on clusters of galaxies, and these are congregations of hundreds to thousands of massive galaxies all held together by gravity. When you see an optical image, you see the giant galaxies, the stars within the galaxies. When you look in the X-rays, you no longer see those individual galaxies because they're too cold to give off X-ray emission. What you see instead is this vast reservoir called the intercluster medium of very hot gas that lies between the galaxies. And there's probably about 7 to 10 times more mass in this hot gas than you see in all the galaxies. So just to show the optical and the X-rays together, this is just a giant puddle of hot X-ray gas, very smooth, very symmetric, centred right in the centre of the cluster. And this primarily radiates in X-rays, and this process called thermal bremsstrahlung. It's also known as free radiation because you notice those two particles stay free of each other. It's not like they're combining, they're just deflecting each other, and so they remain free of each other through the whole process. And so when we look at clusters of galaxies, very hot plasmas, this is the dominant mechanism. And the more dense the material is, the more these interactions are going to happen, because it's going to be proportional to the density squared. And so right in the core of the cluster, you've got much higher amounts of X-ray emission from this process because the material is denser. And so you can track the luminosity and the properties of the X-ray emission. It tells you something about the density profile of the gas within the cluster. And of course, there are other things. You can give a photon energy. So if you have a nice low energy photon, again, just minding its own business, if it gets a kick up the backside from a very high energy particle, so a physical collision between the two, it's going to give that photon more energy, and then it maybe will go off and skip away as a high energy X-ray electron. So imagine that low energy photon is a microwave photon from the cosmic microwave background, the background screen to everything. It's travelling across the universe towards us. It encounters a high energy situation, maybe charged particles and a jet zooming out of a black hole. Those collisions will happen, and you'll get all along the jet, you'll get a process of this boost of X-ray emission where all these microwave photons are suddenly being kicked into being X-ray photons. And it'll highlight where, in the foreground, they're very fast-moving, high-energy particles, so moving at sort of relativistic speed. So again, this kind of radiation will trace very high-energy, very hot regions of the universe. And again, there are other ways to accelerate electrons. For example, with a magnetic field, strong magnetic fields, high, fast-moving electrons, they're forced to spiral around the lines of magnetic field. You're accelerating the electron. If you're making it go into circular motion, it gives off that extra emission gives off that extra energy as a photon of emission. The energy of the photon depends on how fast the electron's moving, and again, the strength of the magnetic field. So you will get this synchrotron radiation, as it's called, right down in the radio, right up to the X-rays. And so again, you're going to get the X-rays from the more violent, the more explosive events. So one such very explosive event might be a supernova. Giant star reaching the end of its life. It can no longer produce nuclear fusion at the core to sustain it against the collapse of gravity. And when these giant stars end their lives, they do it in this spectacular fashion. They blast themselves apart. The core settles down to form something like a neutron star, a black hole. The outer layers of the star are thrown off in an expanding cloud of debris. But there's a blast wave that precedes it. And when you look in the X-rays at this supernova remnant, so what's happened after the star's blasted itself apart, you can see different facets of this X-ray emission. And these are colour-coded according to the energy of the X-rays. We have this thing, very high-energy electrons are called hard X-rays. Soft photons are the low-energy X-rays. So you've got hard is high energy, soft is low energy. Here, this is just the hard emission from the supernova explosion, the high-energy emission. This is where you've got the blast wave expanding out, and those little electrons are getting reaccelerated right within this blast wave, reaccelerated to give off this bremsstrahlen, and in places you can see some tiger stripes here and down here. This is where the magnetic fields are highly turbulent and very concentrated, and you get lots of synchrotron radiation. So this is the high energy emission associated with the blast wave. But then you also have the debris of the star itself, which is cooler. It's just at temperatures of millions of degrees, so this is soft energy emission, and from here you see the debris of the star itself expanding away, and how that blast wave precedes the bubble of material moving out. So again, all these processes can be going on at once, but they come out at different energies, reflecting different aspects of the explosion or whatever event you're studying. And you can tell which is being produced by the spectrum it produces. A spectrum is, so it's just like we split optical light into a rainbow of continuous colour. You can do the same with X-rays. You split it into, if you plot colour against the intensity, you get what's known as a continuum. And it's just the spread of how many X-rays you get of which energy. But all the processes I've talked about will just give you that continuous rainbow of X-ray colour. And there are far more X-ray colours than you get in the visible waveband, by the way. Many, many different colours. You can, of course, produce discrete spikes of light by processes, again, analogous to the visible. We're used to these lovely pink glowing clouds of hydrogen atom that have absorbed energy from starlight. They store that light by exciting the hydrogen atom, and then when they later release it as that pink radiation, and it's always pink because hydrogen is the most common element. You get the same process in all the wavebands. You have your atom, maybe it absorbs energy, perhaps through a collision through an electron, perhaps through absorbing a photon of light. When that atom receives that energy, it'll give the energy to one of the electrons in the outer orbits around the central nucleus, and it'll excite that atom. So effectively that atom or molecule or particle will store that energy for a while, but at some later point it will release that energy. That electron will move from one higher energy level to a lower energy level. And the clever thing is that those energy levels are completely prescribed by the quantum physics of the atom. They only happen at very definite levels, and the electron can only jump from one particular level to another. It's like you rearranging books on a bookshelf. There are only certain places you can put your books. It's the same for atoms with electrons. They can only put electrons at different energy levels. So when an electron jumps from one energy level to another, the energy it releases is given off as a photon. But that photon and the colour of that photon, the energy of that photon, is completely determined by the atomic makeup of the chemical element. And so you get different colours, different spikes of colour, according to different transitions between atoms. Now, as I say, this happens in the visible, it happens in the radio, it happens at all wavebands. The nice thing about the X-rays, again, you are looking at high energy photons. You're looking at large jumps of energy. You're looking at jumps between the very innermost, most tightly bound electrons within an atomic structure, some of the most complicated and heavier elements. So I don't expect you to be able to read these, but this is just an X-ray spectrum, wavelength against light. But each one of these spikes, so you've got things like iron 17, iron 14, very complicated, oxygen. All the heavy elements, so the things like carbon, nitrogen, oxygen, magnesium, iron, have very strong lines within the X-ray waveband for all those inner orbits and energy levels for the electrons. And again, this is going on at the same time as you're producing the X-ray emission from all those continuum processes. So here's another supernova remnant. You recognise the outer shell of accelerated electrons shown in blue here, inside some of the hot gas that's shown in the blue-green. They produce the kind of energy at all wavelengths. But superposed on that, you have these discrete spikes of excited elements within the gas. Here, for example, is the spectrum of Cassay, again, wavelength, energy against intensity. But each of these represents sort of magnesium, silicon, sulfur, oxygen, calcium, iron. Why I'm showing you this is because if you take an image in different colours, you can map out the distribution of these elements within the nebula. This is fascinating because remember, all these heavy elements have been forged right in the core of that star. Many of the even heavier elements than iron actually formed within that supernova explosion when the flood of neutrons are released and new elements form. And you can actually start to map where all these elements are in the nebula. So for Cas-A, for example, you can do maps in the light of sulfur and silicon. You can do maps in the light of neon, oxygen, magnesium, and even iron. And then you can look at their comparative distribution. It's quite interesting when you do this. You notice that iron seems to be on the outside of this. I mean, it's still quite a crude map, but you're still looking at the different distribution of the elements. It's curious that iron's on the outside because when you think of the progenitor to this explosion and the way that nuclear fusion happens in the core of these stars, you expect the very centre of the star to have been made of iron and these other elements to be on the outside. It's almost like the supernova explosion has turned the star inside out, and now the iron's on the outside. So again, there's something very interesting happening within that explosion to produce this distribution of elements out in the supernova remnant. And of course, what you see from a gas, a hot gas, depends on what temperature it's at. So again, these are just spectra. So you've got energy against the vertical direction is just how much of that light is produced. In the top corner here, when you've got very hot plasma, you've just got thermal bremsstrahlung. You've just got particles reacting to the electric field of each other and accelerating each other. As the gas cools, is less charged particles, you start to having, excited atoms and ions. You start to even just get atoms recombining. And you begin to get emission lines. The continuum emission gets weaker, and then if you drop to even lower temperatures, you get very different lines. So what lines are there and what continuum is there tells you something about the temperature of the source as well as the chemical makeup. It tells you all kinds of things about the structure of that plasma. And again, this is something you can only sample in the X-rays. And indeed, some of these transitions are so detailed that modern X-ray telescopes are actually testing our understanding of atomic structure of some of these heavy elements. Here's another example. This is a large cluster of galaxies. You wouldn't know it because this is the X-ray puddle of gas. You take a spectrum of that. You've got the thermal bremsstrahlung from the hot gas. But you also get excited atoms, excited heavy elements within that gas. And the surprising thing is that all this gas that lies between the galaxies, it's not primordial gas. It has got heavy elements in, such as iron. This means that some of that gas that lies between the galaxies has been processed through stars and then spat out by the galaxies into this intracluster medium. It's all been enriched over the timescale of that cluster of galaxies. And understanding what elements are in the gas tells you something about the past star formation history of the galaxies within the cluster, and also what kind of supernova were needed at early times to produce this combination of elements out in the intracluster medium. There are other methods, just very briefly, again, these involve exciting energy levels between atoms. For example, you can have an ion, so a charged atom, that absorbs some energy from a photon, and it loses an electron from one of those innermost, really tightly bound shells. This leaves behind an unstable atom, and one of the outer electrons falls down to fill in one of the energy levels and gives off a photon. Now, I mention this because this can happen with it doesn't have to be a hot environment. You just have lots of powerful energy coming in to excite one of those inner elements. So this gives us X-ray emission from the moon. Okay, this isn't X-ray emission from the moon. This is just in case you forgot what the moon looks like. But if you've got this image of the moon and you looked at it through X-rays, you will see the bright side of the moon gives off a certain level of X-ray emission due to fluorescence. And this is the X-rays from the sun coming and doing fluorescence on the cold material on the surface of the moon. And again, the nature of this X-ray emission can trace the distribution and map what elements are on the surface of the moon from the way that they interact with that incoming solar radiation. So it produces X-rays on the moon. Another interesting way is if you have a charged atom, an ion, and you have another atom. If they collide at high enough speed, they can swap electrons. They can do all kinds of fancy things. This is called charge exchange. So the ion steals the atom's electron, and again, as it reshuffles and stabilizes, it gives off a photon. So this, for example, provides, believe it or not, X-ray emission from comets. Comets are cold. You wouldn't expect to observe X-ray emission from them, but you do. Beautiful false colour image of a comet. Good job I'm telling you that, because it's not instantly recognisable as one. But here you have lots of ions, charged particles in the solar wind coming out, and they interact with the cold atoms that are being given off by that cometary nucleus. And they've got this process of charge exchange, produces X-ray light from that comet. So again, an unexpected result, a cold object producing strong, well, fairly strong X-ray emission within our solar system. And so this is tracing a whole host of different processes compared to what we see in other wave bands. And again, those ones involving the very inner, highest energy levels of the atoms. So the X-ray sky looks very different from the visible sky. This is part of the sky that I hope you're familiar with, or if you won't be, you should be come a few months when it'll be up during the night time. You have Orion, this is the moon by the way, and Sirius and Taurus. It's a very recognisable part of the sky. Now if you look at the same part of the sky, exactly the same scale in X-rays, superficially it looks similar. You can see the 3 stars of Orion's belt and his sword. But if you start to look in detail, you find there isn't much correspondence with the rest of the image. And that's because in the X-ray waveband, you're looking at very different sources. So here, you're seeing stars. You're seeing, well, and the moon, but you're seeing stuff that's being powered by nuclear fusion at the core of stars. In the X-rays, you maybe see, you will see these stars because they're young. Young stars are active, they're hot, they're producing lots of X-rays. The moon, for example, here now moves to a very dim source. This bright source is actually a pulsar, so something that's accreting material. We'll come on to that. You can see, here is Sirius. In the visible, you're seeing a giant companion. In the X-ray, you're seeing the invisible compact companion that's accreting material. And similarly between these, when you look in the X-rays, you are seeing more or less lots of sources where the energy for this light is being provided by material falling under extreme gravitational fields. It's not nuclear fusion, it's a completely different process giving energy. And the other thing is that X-ray sources flicker and vary. We're used to optical sources not changing much. X-ray sources, all of these are powered by unpredictable flows of matter falling through gravitational fields onto compact objects such as neutron stars, black holes, white dwarfs. Because you're relying on that unpredictable supply of material, the sources flicker and change. So this is a speeded up view of the sky. The sky is unwrapped and the galaxy sits in the middle. Blue indicates very high energy sources, red low energy, green intermediate. This is the progress of the sun across the sky, because obviously it's speeded up in time. But you can see how the sources, here I'm just identifying a few of them, are flickering on and off. Some with a regular pattern, some go dormant for a long while, flicker on. And it's all because, you know, the fuel supply is changing, therefore the accretion is changing. And so that's a very key difference between the visible and the X-rays. To actually obtain these X-rays is not straightforward. You saw how they were absorbed by the flesh and bone of a hand. They're absorbed by a few meters of air. For this reason, X-rays don't make it down to the ground. That's actually quite a good thing, by the way. But you have to go at heights above about 80, 100 kilometres to start to receive X-rays from the sky, ideally right above the atmosphere. And the way you do that is you have to have flights. And flights on rockets, initially, perhaps in the 1940s, on Captain V2, German V2 rockets, such as this one launching from near White Sands in New Mexico. And this is what has delayed, in a sense, the start of X-ray astronomy. We knew the sun was a strong source of X-rays. It wasn't clear that there was an X-ray astronomy out there. And this only changed in 1962 with the first mission that was flown up on a rocket. And it lasted probably about just under 6 minutes above a height of 80 kilometres. And it wasn't very sophisticated. The detectors, you can just see two round things, one there and one there. These are two Geiger counters. And during that under 6 minutes, it more or less just scanned the sky, taking a view of the sky. Now, ideally, it was looking for this X-ray fluorescence on the moon because it was predicted to happen. What they discovered that wasn't the brightest source of X-rays. There was at least one other very bright source of X-rays, we now known as SCO-X1. And this showed that there were cosmic objects out there that produced X-ray emission. There was an X-ray astronomy to be done. Now, the leader of this team was Riccardo Giacconi. He was shown with a later mission from the 1980s called Uhuru, and he won the Nobel Prize of Physics in 2002 for this development of this new science of X-ray astronomy by showing there were these other sources out there beyond the sun worth studying. Of course, now we know of hundreds of thousands of X-ray sources across the sky, a whole range of sources. And we don't use rockets anymore except to get our telescopes out into space. So the best place to do X-ray astronomy is out there on a satellite. And there are many missions. There have been many missions. Current ones, we use Chandra at the lower end from NASA. We've got XMM Newton from the European Space Agency. There are various Japanese missions that astronomers will use. It's an international collaborative effort. But the key thing is, X-ray telescopes are very different from optical telescopes. Now, optical telescopes, you have a dish which reflects the incoming radiation to a mirror and to a focus where you can put the eye. X-rays, that doesn't work. They're high-energy photons. They're easily absorbed. If you have your reflective dish, think of an optical mirror, your X-ray comes in, it'll just get absorbed. An analogy might be to think of bullets. Fast-moving bullets, if you fire them directly at a wall, they get absorbed. It's the same with photons. Fire them directly at a dish, they get absorbed. The difference is, with a bullet, is that if it grazes the bullet, if it comes at a very shallow angle, it will ricochet off. It's called a grazing incidence. It doesn't actually get absorbed, it gets reflected at this very shallow angle. This ricochet can also apply to X-rays. So if you have your mirror oriented not like that, but almost parallel to the incoming radiation, the X-rays can just kiss the wall and get deflected, kiss the mirror and get deflected in that way. Again, think perhaps of skimming stones on a pond. If they go in too deep, they go down through the water, but if you get the angle right, they will skip and bounce. And to do this, as I say, the X-ray mirrors have to be almost parallel to the incoming radiation, and if you have two surfaces, it'll do two reflections, which will bring it to a focus here. And you don't just have two mirrors like that, you in fact have a ring all the way around, and so you're collecting radiation all the way around. But of course you have a problem because there are an awful lot of photons you're missing. You're not presenting much of the mirror to the incoming radiation. And the way you increase the amount of photons you can collect is not just by having one ring mirror, but to have a whole host of them, all nested one inside the other. And from this you can collect all the photons and bring them to a common focal point. So X-ray telescopes consist of long cylindrical tubes, and these tubes have to be very lightweight because you're going to launch them on a rocket. They have to be coated with inert materials such as gold to minimise the interaction between the X-rays and the material coating the mirror, have to be highly reflective, and they have to be very precisely moulded. And in terms of modern X-ray telescopes, you might look at this diameter being about 1 metre, and the distance to the focal point being up to 10 metres away. Very long structures. I have in fact, I know you don't normally do show and tell at Gresham lectures, but I did bring you an X-ray telescope mirror, which you're welcome to look at afterwards, and you'll be able to see the change in angle of the structure. This is a flight spare from a mission called Beppo-Sachs, which was launched in 1996, and it's just one of about, trying to remember now, it's probably about 30 mirrors, all nested inside each other. And this is a Diddy telescope. The focal length is only about 1 metre 35, but you had 4 of these sets of 30 nested mirrors. So you're welcome to have a look at that later. And this is the business end of a telescope, all those nested mirrors, and this is where the X-ray photons come in. So what do we study? Well, Ordinary stars like our sun are kind of a bit of a no-no. The sun's bright because it's close. You can see other ordinary stars because they're close. So this is Proxima Centauri in X-rays. You're only really going to look at ordinary stars like our sun if for some reason they've got a lot of solar wind and you're looking at how the material flowing out from the sun is interacting with its corona, maybe producing shocks that reaccelerate electrons and produce X-ray lights. But in practice, ordinary stars, as soon as they get a few light years away, are not strong X-ray sources. Young stars are, though. If you remember those stars in Orion's belt and down in his sword, young stars are much more magnetically active, and this produces, again, reacceleration of particles and strong X-ray emission. And they're also a bit variable. They will flicker on and off in X-rays. So here's a nebula. These blue stars are young, very massive stars, newly formed within this cloud of gas and dust. If you look in the X-rays, you no longer see the gas and dust because it's too cold. But here you can see individual red light from very active young stars and perhaps some diffuse hot gas where they've heated the gas around them or from their solar winds. Or similarly within the Orion Nebula here that we're familiar with, in the visible, and zooming in right to this bright core here. So you've got, again, you can't see much, there's just so much gas and dust in the way. But remember, that doesn't radiate, and high energy photons can just go straight through that, and you're left with the light from individual stars. So we can study the X-ray emission from very young stars. This is a bit of a problem, because remember, even young stars like our sun, so not even very massive stars, appear to be more X-ray active when they were younger. So this is when perhaps they're forming planetary systems. So we're having enough trouble understanding how planets form around stars. We've also got to counter into that the fact that the star might have been much more X-ray active at the time, pumping much more energy out into its environment. And not just X-ray energy, even jets. This is a very young star. It's about 1 million years old, and it's a similar mass to our sun. And you can see in the X-rays it's producing these two jets. And to the eye, I wouldn't say of a believer, but you might be convinced that there's something blocking the light on the counterjet as opposed to the near jet. And the interpretation is, artist illustration, is that around this disk you've got one of these disks of material that's forming a planetary system, and that's blocking the counterjet relative to the near jet. And so you've then got to add into the fact that maybe stars like our sun pumped out jets of material early on when they were forming stars. Again, confusing the issue enormously. Supernovae, well, I've talked about young ones having this high blast wave that comes out. These are ones that are perhaps hundreds of years old. You get much older supernova systems that are 1,000 years old. It looks like that blast wave has then been overtaken by the cloud of debris. You've no longer got that clear outside rim. But you do get something interesting happening around the pulsar at the middle. So this is the collapsed core of the star. These are covered with a magnetosphere of charged particles, strong magnetic fields. You've got a wind, it's called a pulsar wind, that comes off this neutron star. And again, you only know it's there from X-rays. High energy matter and antimatter particles, charged particles, spewing out into space around the neutron star, colliding with its environment. Here's the Crab Nebula in the visible. So again, this is an exploded star. In the X-rays, you can see this pulsar wind. And it's such a beautiful picture. I'm going to zoom it up. There's the pulsar jet. And then this is this cloud of high-energy particles being thrown out. And you're seeing shock waves where it's interacting with the surrounding material of the debris. Again, very different kind of physics, understanding those kind of interactions. And it's through X-rays that we first discovered proof of a black hole. And this is Cygnus X1. It was discovered soon after SCO X1. The way the naming goes is that Cygnus just means it's the first X-ray source in the constellation of Cygnus. And when this was discovered, you couldn't pinpoint its position on the sky completely accurately because the exact direction of the source was still a bit crude. Except that this source underwent an X-ray flare at the same time as it also underwent a radio flare. And at that point, the radio position was much better determined. And assuming both those those flares came from the same source, it allowed them to pinpoint the source of the X-ray emission. And the problem was it was a star. a blue supergiant star, about 18 times the mass of our Sun. Yes, it's hotter than our Sun, but it shouldn't be giving off strong X-rays and flaring. So they followed it up in the visible wave bands, and they found that it showed a shift in its spectrum. This is the Doppler shift, meaning it was coming towards you and away from you. So it's rotating around something with an orbit of 5.6 days. You can't see its companion, and yet you can work out the mass of being about 10 solar masses due to the movement of this other star. You can look at the energy output in the X-rays right down to the radio, and the only practical consideration was that it was a black hole. So this was the first indication that X-rays are emitted in the vicinity of black holes. So you can't find a black hole if it's in the middle of nowhere, but where we do see them and where we study them through X-rays is where they have material around them that they're accreting. So one example could be within a binary system of stars. Imagine you've got two stars, one slightly more massive than the other. A more massive star goes through its evolutionary cycle quicker, runs out of fuel, throws off its outer layers as a supernova, the core collapses down to be a neutron star or a black hole. The second star, chuntering through its life, finally runs out of the energy. Oh, by the way, the supernova explosion, surprisingly, doesn't always disrupt the binary system. It depends on the relative mass of the two stars. But assuming it hasn't been disrupted, eventually this will swell up at the end of its life, become a red giant, more distended, and those outer layers are not held on so strongly by gravity, and they're vulnerable to being pulled off and tugged and accreted by the compact companion, whether it's a black hole, neutron star, or white dwarf. And this is a very strong source of X-rays. The material, as it forms the accretion disk, whirling ever faster right down to the core of the black hole. Remember, it's not the black hole that's producing X-rays, it's the material accreting onto it. And not just that, you'll get energy, you'll get material in the disk being heated up, where it impacts from the star onto the disk, you'll get X-rays. And of course, trying to disentangle this in a moving system, when you've got all these different sources of X-ray emission within the system, can be quite complicated. But it tells us a lot about the life cycles of binary stars and stars in general, and it allows us to study black holes, stellar mass black holes. So when you look at a galaxy, an ordinary spiral galaxy in X-rays, you don't see the stars, you see these compact companions, you see what those massive stars have become. And so here's the centre of the Andromeda galaxy. All of these bright sources are compact accreting, endpoints of the stellar lives. Similarly, here's a nice big spiral galaxy fairly close to us, massive stars forming the blue spiral arms. In the X-rays, you see just where those have become compact objects, neutron stars, black holes. So the X-rays tell us about the past stellar evolution of a galaxy. And it's the same with our own galaxy. You look at it, and everywhere you see sources that are individual black holes. This is, again, stretching, looking along the line of our galaxy, the disk of our galaxy, lots of individual sources, hot clouds of gas that have been heated by supernova remnants, especially where those supernova bubbles join up. Right in the core of our galaxy here, there's an X-ray source that is associated with a supermassive black hole. Black hole at 4 million times the mass of our Sun, right at the core. And it's not actively accreting at the minute, but you can see perhaps there are these lobes of heated gas to either side, suggesting that it has gone through periods of activity in the past. And even this morning I was reading a news item that showed that it had undergone a slight X-ray flare. So again, that gives us a way of monitoring the past and current activity of the supermassive black holes at the core of our own galaxy and other galaxies. So you have your accretion disk, material, you get X-rays where the material hits the accretion disk. As it warms and moves faster, the X-rays come sometimes, not all accretion disks get hot enough, but sometimes just from that inner vicinity of the black hole. And this is why the X-rays give you the best sampling of the most distortion of space and time due to relativity. You get as close to the black hole as you can. And there are other weird things that happen. When you have a black hole, not all the material goes down onto the black hole. Some is squirted out the last minute as jets. You've got strong magnetic fields moving at relativistic speeds in a rotational manner. This creates dynamo, some kind of motor which can spit out charged particles at the last minute in twin beams of radiation. Now, again, relativistic moving particles, charged particles, they're going to produce radiation. And sometimes the key indication is a black hole at the core, if it's accreting, either in a binary companion or a supermassive black hole, are these jets. And here, for example, in the optical, you've got no idea that there's a supermassive black hole right at the centre of this rather strange galaxy. If you move to the radio, you'll see some of this non-thermal, these accelerated electrons giving off radiation. And in the X-rays, you'll also see the hot gas in the galaxy, but also right along the jets, electrons being re-accelerated, being reheated to produce this strong X-ray emission. And again, you can do some really interesting physics around the black hole by looking only in the X-ray wave bands. Now, as I say, not all the X-rays are produced in the accretion disk. It's something to do with the jet generation, but they tend to be produced just above and below the accretion disk. Now, some of that light will come directly towards you. Some of it gets reflected off the accretion disk. Charged atoms rotating around the accretion disk, they absorb a photon. You've got an ion, so that's an ion of the element iron. It can absorb the X-ray photon, and it can give off, it's got fluorescence, it will produce a line of radiation, so a spike at a certain colour. Now, if it was just a cloud of gas and you're radiating with X-rays and it gives off this iron line, you would get a nice peak, just one iron line. The fact that it's in a spinning accretion disk around a very massive black hole means it doesn't look anything like this. First of all, you've got basic Newtonian effects. Some of the disk is coming towards you, some away from you. You get light from both sides, so this line gets shifted to a blue peak and a red peak. So far, so good. Then you also have the fact that it's moving at relativistic speed, so you get relativistic bleeding of the side that's coming towards you relative to the one that's going away, so you get enhancement of the blue wing. And then you've got effects that you've got the strong gravity. The photons lose energy climbing out of the gravitational well of the black hole. And so everything gets shifted down towards the red, that way, to the red. And then all of this is blurred because it depends on inclination, it depends how fast the black hole is spinning. Now, these are theoretical models of what happens to the iron line from the material in this disk. And you can, from these, tell something about whether it's spinning, whether it's not spinning, how fast it's spinning, what the inclination is. You can also observe this. Now, this is one of the more recent developments where you have the theory that is then matched by the observations. You can characterise the environment and the black hole in both stellar systems and supermassive black hole systems at the core of galaxies. And then, finally, just to show you that the other thing that was discovered 50 years ago is it wasn't just that there were X-ray sources out there, but the sky is not dark in X-rays. Here's a ROSAT, this was a German X-ray satellite from the late 1990s, view of the moon. This is the fluorescence of the sunshine on the moon's disk. But here, this is the X-ray background. There's a diffuse glow across the sky. And at low energies, this is just a map showing the low energy X-ray background. It's all over the sky, and it's thought to be due to near bubbles of hot gas. That's easy to understand, but you also get this glow at hard energies, high energies. And it's only recently that we've begun to resolve this into discrete sources. And this is thought to be very distant, so long time ago, versions of galaxies when they were still accreting. And the soft X-rays have got absorbed by the intervening matter. Perhaps these are early stages of galaxy growth and they're enshrouded by dust. The soft X-rays don't get out, but the hard X-rays are the only X-rays that get out through that obscuring matter, make their way across the universe towards us. And so by looking at this hard X-ray background, we're looking at all the activity, all those past supermassive black holes at the very earliest stages of galaxy formation. So even just studying this diffuse light in the background sky tells us something about the prehistory of the galaxies we see today. So really, there's an awful lot that I haven't told you. Trying to pack all of X-ray astronomy into sort of 55 minutes is a challenge. But anyway, I hope I've given you a flavour of how it's a very different kind of astronomy, very different kind of processes than we see in the other wave bands. And then just to put a flyer, we're going to go from the extreme to the much more local. I'm going to be talking a bit more about optics within our own atmosphere and talking about atmospheric phenomena at the beginning of December. Thank you.
For all information, please visit www.gresham.ac.uk.